Welcome everyone to the SRAI tutorial, so introduction to the machine learning with SRAI. Yep, there are quite a lot of you here. It's a big venue also. Hello, good that you came here to actually listen to us and to learn maybe something. I hope you will learn something from us. So hello everyone, and let's roll. So here is the link and the QR code for our resource materials. You can follow along if you want, but if you didn't prepare the repository earlier, then it would be kind of hard to set it up right now. It will be time consuming, and I think that the Wi-Fi will just die because there is a torch to download. So I don't recommend to run the repository right now, but you can run it after, or just look that up, or follow us. Follow the PDF. There are PDF exports in the repository in the exports folder, so you can look that up on your site also. Okay. Did anyone want to? Okay. I think everyone. I hope that everyone managed. If not, then I can always come back to the link or to the QR code. Just let me know. Okay, so let us introduce ourselves. We are Kraina.ai, a geospatial and mobility group at Wrocław University of Science and Technology in Poland. And basically, we tackle geospatial problems, and we try to make some solutions to overcome the obstacles that we encounter there. Here are our beautiful faces. We have a supervisor that's the head of the team, Piotr Szymański, who is also a lecturer in the Wrocław University of Science and Technology. And also he is an urban activist, and he manages all of us. And some of us are here listed. This is me, Kacper Leśniara. And here is also Kamil, Kamil Raczycki, Piotr Gramacki, and Szymon Woźniak in the corner hiding. Yep. So how did we actually form the group and started SRAI? You will know what SRAI is in a moment, but what are the origins basically of Kraina and SRAI? So we started with our thesis, master's thesis, around geospatial domain and representation learning. And we encountered a lot of obstacles and challenges with working with the data and coming up with the embeddings, let's say. And we kind of assembled our work that we did separately, and we assembled the work that we did under a, let's say, common library, which is called SRAI. Yep. So basically, SRAI is a spatial representations for artificial intelligence, which basically is a toolbox that aids you with working with the geospatial data and domain. Okay, here is our website for Kraina. You can visit it if you want. It's kraina.ai. Here you can find some information about our projects that we did or are doing. Here you can find some, for example, some news. Yeah, the cookies are a bit on your face, but yeah, here you can find some news that are updated regularly. You can look into our team. You can look into our publications that we did and some resource materials also. And if you want, and we encourage you to, you could contact us at this mail, so contact@kraina.ai, or just fill in the form and we will reply to you as soon as possible. Okay, so what you will get out of the tutorial, we hope. So we want you to get familiar with the geospatial domain. We want you to have the tools and knowledge to work with the spatial data, and to know how to actually apply the methods, the functions to the spatial data to get what you want to get. And of course, we want you to get some SRAI library know-how. And what is the roadmap for that tutorial? So firstly, we want to make a brief introduction to the geospatial domain, because There are a bit of concepts, a few concepts that you need to get familiar with. We want you to get on the same page and yeah, basically to know why did we come up with SRAI and what are we building around the geospatial domain. Then we will talk about the SRAI library itself, its API, design, interface, how to use that, etc. Then we will show you the machine learning example for that and show you a business use case, hopefully funny one. And yeah, there is also a fifth, because all of these are notebooks that will be shown as slides. There is also a fifth notebook that we won't show probably here because there is not that much time, but you can look that up in the resource materials itself and run it and see what you get. Okay, there is a QR code for the Telegram topic channel where you can post the questions. What can you do there? Yeah, post the questions to talk, and we will try to answer all of your questions here. Maybe if you have some right now, then I can answer them, or maybe should I show the link to the resource materials? Anyone wants that? Yes? Do you want the link to the resource materials? So the tutorial? It's okay. Okay. So yeah, I'll pass that right now to Shimon then. Here we go.
Okay. Yeah, I think you can hear me. Okay, thank you, Kasper, for the introduction. I was tasked with introducing you guys to geospatial data, and given the time that we have, it's a really hard challenge because there is a lot to cover, so fasten your seatbelts. It's going to be a ride. No, but jokes aside, we're not going to go in deep. We encourage you to check out this tutorial by Joris that covers the introduction to geospatial data analysis much more in a much more comprehensive way. Yeah, it's quite good, and it aligns well with what we're showing you here today. So let me first ask you, how many of you have worked with geospatial data at all? Like for work or for research? Okay, I see some hands. And how many of you have maybe seen the tutorial here? The one? Okay, 2 hands, okay. So I think this might be beneficial to some of you at least. So this introduction here should familiarize you with some concepts. This is more of a brief overview of some selected concepts from geospatial domain rather than a comprehensive introduction. But we'd like to build the vocabulary for the things that we'll be showing you next. It will hopefully allow you to understand the APIs of the library that we built, the different parameters that are there, and so on, and maybe some of the inner workings of it. And also, it covers some of the GeoPandas, and it's a great tool for working with pre-post processing of data for the library, and the data preparations, analyzation, and visualization. Yeah, so as I said before, we utilize GeoPandas under the hood. It's actually one of our main libraries. We built on top of GeoPandas. We don't try to replace it. We don't try to reinvent the wheel, as we think it's good as it is. We like to fill in the gaps with some of the domain-specific things from machine learning. Yes, and we try to, our APIs either take as input or return geodata frames, so it's easy to use GeoPandas functions after all of that. Okay, so what's GeoPandas? So the ones of you who work with geospatial data, I think you know what it is. It's an extension of Pandas that allows working with spatial data. It extends the standard Pandas data frame API with geometry column, and a lot of tools for working with spatial data. yeah, it's open source. It really simplifies working with the data. And yeah, so there's that. And the geodata frames, as I said, are an extension of pandas data frames with the geometry column and the standard properties of that add meaning to the geometries themselves, or describe them otherwise. So let's look at an example. Just adding here that GeoPandas can load a number of different formats and so from different sources, but we'll be using a shapefile here. Please don't worry if you don't understand any concepts here. It's really, as I said, if you want a deep understanding of the domain, please check out the tutorial link before. Okay, we'll be loading a shapefile with countries. So here's what it looks like. And as I said, it's a data frame with a geometry column. There are some standard columns with some data, and geometries that describe where and what the area or point or line lies, and what it looks like. Yeah, we can visualize them in two ways: in a static way or in a more dynamic way. A static way uses matplotlib with the plot function on the geodata frame, and explore allows for a more interactive way to work with the data. You can view the shapes and the metadata. I don't think, well, there is metadata. I don't think you can see it there. Okay. So as I said, we are working with a data frame. So those familiar with pandas will know that the API should be familiar. So that's what I wanted to say with this slide. So we can use different pandas operations for on it, just as calculating the mean of a numeric column or value counts of a categorical column. So we can see here that the mean of the population estimate is this number, and then the number of countries per continent here. Yeah, and the differentiating factor is the geometry column, I would say, aside from the functions for working with spatial data. And as you can see, it's implemented as a geoseries, and as shown before, it contains some multi-polygons and polygons that describe the geometries. We can use it to calculate the area or use all the different functions that are shipped with GeoPandas there for this column. It's a bit different from the standard numeric and categorical variables. Okay, so now that we know that there's GeoPandas, we can go a bit deeper to understand what the geometry column is, and it is implemented using Shapely to describe the geometries. And here I've chosen two countries, selected them from the data frame, Poland and Germany, and I merged them just to form one shape. And here's what it looks like. When we go further, we can see that it is a Shapely polygon. It's one thing from the geometry column is a Shapely. Well, it can be a polygon, it can be a point, a line, another different geometry. We can use some properties of geometries. They are specific to the geospatial domain. With area, we can check the bounds, so the minimum containing rectangle of the geometry. We can also create geometries manually, and here it is a line that goes across diagonally through the two countries. I used bounds for it and constructed a line string just to show you that you can do that manually. We can view that, and here's what it looks like aside from the broken projection. So a line on top of the two countries. Okay, one more thing are Spatial operations, that's also shipped with Shapely, and they can also be used in GeoPandas. So predicates such as within, intersects, you can use that to check whether geometry intersects with another geometry, or that it's contained completely within the other one. So as you can see, the line isn't, and we can see that here. It isn't within the area, but it does intersect with it. And we also can do the same thing on geodata frames. So we'll just prepare some data to show it. OK. And yeah, so one more concept I need to do that, and it's only for the introduction of this concept per se that we'll be using after. Here you can see 3 different types of spatial indexes. These are, I would say you can think of them as an analogy from database indexes, so that you can index into space efficiently. So, for example, I think all of them, but for example, H3 I'm most familiar with. It covers the whole Earth with hexagons and some pentagons, I think, of different resolutions, and then assigns them a unique ID so that you can index into the specific areas of the Earth. And we introduced that, so we'll use it later, but just for you to know, there is a thing like this. Yeah, and as I said, H3 is a hexagonal grid, and it can be subdivided approximately into finer hexagonal grids. And so just to come back to what we were doing, we have this example of a line and a geometry, and what we'll do here is we'll split the geometry into regions, H3 regions, just to show you that you can use spatial predicates on geodata frames as well. So just because these are Shapely polygons, polygon and line string, and you can also use the predicates on geodata frames. So quickly, here we've got the geometry. We regionize it with H3. We split it into regions. And it returned a geodata frame here. And then we used the intersects predicate on the line, so a geodata frame and the Shapely line. And here we plotted the predicate results. So the line crosses across all these different shapes here. OK. And the last thing I'd like to introduce are spatial joins. And these are, again, can be analogous to what you can do in databases, so that if you have 2 sets of different geometries, you can merge them using different predicates. For example, here we, again, took Czech Republic and created some regions. Prague created some regions, and after that, we'd like to get some more data. So here we've got the regions. OK. And also, please don't worry about the tools we use here. They will be described further. They are only for showcasing the concepts here. So we download some data from OpenStreetMap for bicycle rental stations in Prague. And an example of what you can do is with that. So if we perform the join, we had the area split into regions, and then we had the bicycle stations. And for example, we want to calculate how many of the stations are in each region, and we can do that with a join. So we use sjoin from GeoPandas to merge the 2 data frames together. And we get the result that has each region with its corresponding bicycle stations that are within the polygons. And to further to calculate the number, we can just use standard pandas code. Yes, so to sum up, I know it's been a lot. I'm sorry for it being a bit too quick, I know. But we covered some functions from GeoPandas, some APIs from GeoPandas. We shown a bit of Shapely. We've seen spatial indexes and spatial operations, and it is all used by us, and it will be useful, I think, for your journey in geospatial domain and for your understanding and for this tutorial in general. Okay, so that's it for this part. Okay, if you have any questions to that, you can ask them now. Yeah, I don't see any hands, so thank you.
Okay, 1, 2, 3. Good? Yep. Okay. Okay, so let's talk about a bit of about SRAI and its design, usage, and basically architecture. So you will be able to handle the geospatial data. So just as a recap, what is SRAI? In general terms, it's a toolbox for geospatial AI that aims to standardize the domain. So we want to provide you a set of functionalities that you will be able to use to work with the geospatial data. And I hope that you can see that. I can enlarge that a bit. Yeah, it's better probably right now. Okay, so there are 4 main components to our library, and our library is centered around the idea that you want to get from, let's say, end-to-end example. So from the string or the name of the location. So let's say Wrocław in Poland. You want to get from that to the actual embeddings, to the actual representation for use in later, like in downstream tasks. For example, I don't know, to predict the house prices in the estate market. And for that, we built 4 main components. So we have the loader, the regionalizer, the joiner, and the embedder. I will talk about them in the following slides, basically. But the main concept is that you want to take the string, the name of the location. You want to convert it somehow to the region, as you may have seen from the previous examples. You want to put that into the loader that loads the data about the region or the features that are available in the region. You want to regionalize it, so split it into the smaller regions, micro regions, using a couple of regionalizers. You can do that. You then want to join these two outcomes and basically intersect them, and apply all of these 3 into the embedder. And in the end, you'll get the representations for a particular micro regions that you can use to influence your work. So let's talk about how to actually get these 2. So the area from the string and the data from the loader to get the features. So let's specify a city. Let's say we want to specify this city, so Basel in Switzerland. And yep, so we have an area name, Basel, Switzerland. Then we can use our utility function, which is basically a wrapper on OSMNX. I'm not sure if you're familiar with that, but we incorporate this library and use it heavily in our library. So let's say we want to get the area for the region. You will use the geocode to region function. You supply the area name, and then you can use the explorer to actually show the polygon, and it's that quick. So you get the polygon around Basel, so basically Basel. Yep. And if we have the polygon, we want to download the data for it, the features for it, we can use the loaders. So basically loaders load the spatial data from different sources. There are a couple of loaders that I will talk about. We wanted to unify loading into a single interface, so there is a single class, or multiple classes, but they inherit from a single class. And you can easily change the loaders, and you will download the data from different sources or in different formats. And the loader's main purpose is to prepare the data for the embedding methods. So you got the features that you can later use in your machine learning use case. So there are a couple of types of loaders. We have a GTFS loader, which loads the public transportation data from the given polygon or from the given area. I will show the example later. We have a couple of OSM loaders, as you can see. So we are biased towards OpenStreetMap in particular because it's a great source of the public and free data. So it's an open source data source, and we use it heavily. And one of the use cases, let's say we want to create a city poster of Basel. So in our library, we give you a couple of filters. So that is basically a dictionary, a set, no, not a set, but a dictionary, but a collection of features that you can use from the OSM. For example, this one is base OSM group filter. So it contains a couple of filters, actually a lot of them. So for example, you can get the airports, the helicopter airports or spaceports or education. So you can get kindergarten or library or etc. basically. So you can get a lot of features, and there are more than that, I think. But for this use case specifically, we want to get only 3 of them, which is we will use the OSM PBF loader. In this case, we want to get these features. So highway, which is basically a road network, and water and waterway. So any water entities, let's say, in the city. And we want that to apply. We want to apply it to the area that we created earlier. And as you can see, we get the features, feature ID. So this is the index. So this is the roads, as you can see. What's that? Okay. Then we have some geometry. So these are lines. And we have the features that we specified above, so highway, water, and waterway. For example, highway can be residential, can be track, can be highway, I think, can be primary, secondary, tertiary, etc. Okay, and let us see the data that we downloaded. So this is the road network for Basel. I'm not sure if there are pedestrian walkways in there, but certainly there is. This is a drive infrastructure and maybe bike infrastructure also. But I think with highway 2 we get all of the roads. I'm not sure. Okay, and let's plot the poster from that. So we will use matplotlib from that and our utility function, and we will say the figure, and we will get the poster of Basel. So yeah, you can of course print that and put it on your wall. At the top of the notebook, you can specify your city. Your mileage may vary with the poster generation, as it's not that solid. But if it's a vertical city, then it should work. But for Wrocław, the fonts or the text is overlapping each other, so you may need to tweak something. Feel free to mount that on the wall and send us a picture. Okay, we have a second loader, which downloads the public transportation. And yeah, we'll use the GTFS loader in this case. And we will geocode Vienna in Austria. We will get the GTFS for Vienna, and we will load that with our loader. and show what we actually get from that. So what we are getting is like the index stops at a certain time, let's say, and we get the features, which means like trips at 0, it means that there are 2 trips at noon, right? Noon, I'm correct. Or trips at 4, it's 0 trips at 4 o'clock. And we get also the directions, and we get the geometry, which isn't shown here, unfortunately, but it will be shown in the later slide. So we can plot or show the trips at 4 p.m., hopefully, yeah. And we can see that with the blue color, there is a lot of stops, or a lot of trips at this stop in particular. So there are 54 trips at the stop that I'm not sure what is it, but you may know actually what's the stop if you live here. Yep, and yeah, you get for all of the area for the whole area you get the stops in the city. Sorry, this is Vienna, not Basel. I'm very sorry. Okay. Okay, so I talked about area and loader. And now let's talk about regionalizers a bit. Okay, so regionalizers are used to unify methods for dividing the area, the whole area into smaller regions, microregions, and they can be based on spatial indexes that Szymon mentioned. We have a couple of regionalizers available right now. So these are Uber's H3 regionalizer, which divides the area into hexagons. We have S2 Google's regionalizer or method of dividing the area. So that divides us into the squares. Both of these methods are hierarchical, and actually they are spatial indexes. We have also our custom Voronoi regionalizer, which basically is a method of data-driven regionalization. So you can see, you will see the example later down the line. And we also have an administrative boundary method. So you can get, for example, counties, districts, countries, continents, etc., out of the OSM, right? Yep. So OpenStreetMap. Okay, so let's look at the spatial index regionalization. We will use the H3 regionalizer, and let's plot that. So with these couple of lines where we specify the resolution for the regions that we want and on which area we want to work on, we get the regions here specified. These are H3 regions. So, and as you can see, there is an index assigned to the region, so it is universal across all of the people, instances, runs, etc. You can point someone to the specific region, and he will be able to find it, and also go up and down in the hierarchy. And to remind you, we want to actually find the representations or the embeddings for these regions, so then you can send these representations to other people, and they can use them universally with their code. Okay, so that was H3. By the way, interrupt me at any time if something is not clear. I should have mentioned it earlier, but if there are some questions, stop me at any time, and I will try to answer them as best as I can. Not many other. Okay. So let's talk about the data-driven regionalization. So we want to make use of the loader, so OSM online loader, which downloads the data through the API, ProtoMaps API in particular. And we want to get from the OSM online loader from OpenStreetMap, we want to get only the stops in Basel. So these are the stops in Basel. There are a couple of stops. These are public transportation. I'm not sure if it's that tram bus. I think that's all. Yes. Okay. And we want to, for these points, we want to use our Voronoi regionalizer to actually seed, to make the stops our seed for the Voronoi, and transform for our area to get the regions, and we can plot them. It may take a bit of time. No. And you will get the regions based on the points that we specified earlier. As you can see, for example, there should be a point around here somewhere. So in this area, it is closest to this point. That will be somewhere here. For example, for this area, the point will be somewhere there. So it will be in this region, it will be the closest to this one. Actually, you will see a usage of this one in business later down the line. And also you can get the administrative boundaries for some countries or cities. So in the example here, we specify an admin level, and we get the, I think it's called suburbs here, or districts, I'm not sure, but you get a bunch of regions, Amring, Isolin, etc. Quite easily. Okay, so we talked about these two things. Let's talk about the embedders and the joiners right now to get the embedding out of all of the data that we gathered. So embedders basically unify the methods for mapping regions into a vector space. So you want to get the regions with the features and transform it somehow to get a vector with the embedding. And we have a couple of them. We have count, so basically counting the occurrences of a particular feature in the region. We have contextual, which takes into consideration the neighbors. We get GTFS to VEC, we get Hex to VEC, and we get Highway to VEC. And we can get the highway. These three are methods for converting the GTFS to the vector representation, hexes with some tags, and basically a road network. So we can try to get some simple embeddings. Let's use OSM PBF loader, H3 regionalizer, some kind of a filter that we have specified, and get the features and regions, not emojis. Okay, we got them. We want to intersect them basically, so we want to make a joint representation for the regions and features to assign a particular feature for a region. And then we use the count embedder, so the simplest one, and we transform the regions, features, and the joint representation into the embeddings. And for example, we get for this region, we get a count for the occurrences of a specific features in it. And this one is kind of empty, but the second one has, for example, 7 benches in it. So you can use that embedding. I'm not sure, maybe to find the parks. Okay, let's plot the bicycle parking. So one feature of all of these. Let's plot just a bicycle station, I think it is. And you can see that in this region there are 13 of bicycle stations. And yeah, basically it's shapes some kind of in shape of a banana, let's say. So this is the main hotspots for the city. These are the main hotspots for the city in terms of bicycle parking, but there are also some occurrences on the outskirts. Okay, so what are we working on right now? We are trying to get to the point where we can give you the pre-calculated embeddings, so you don't have to go through all of the stuff that I showed you right now, but you can just say, I want the embeddings for that region, and we will supply that to you. You will probably have a selection of models that you can use from, or like selection of embeddings from these models. We want to make sure that you can easily fine-tune the models that are in the library. because you may want to tweak them a bit to accommodate to your use case better. And we found that there are not a lot of data set and benchmarks standardized in the geospatial domain that you can test on. So we want to make sure that we supply that for you also. Any questions onto that one? Yes, the microphone can. At the last one, yeah.
So you showed the map with the plots of the polygons with the least distance to the individual points. Do you get easy access to stats like area or other stats of these individual polygons?
Yeah. You can, using GeoPandas, basically, if you have the polygon, you can use the dot area, and you get the area. You can calculate some mean, etc. So, but if you want to, for example, get a population in this area, you need to get that from other sources.
Okay. Thanks.
Any other questions? Yes.
Is there any easy way to add time to the data points? So, for example, I would like to see the change in time, for example, number of bikes in the area.
Yes, I think so. I mean, you can add the time into the pandas itself, so you can have multiple entries for the same station in time, basically, and you need to plot that somehow if you want to see that. I'm not sure if you can plot the time, like the timeline on the bottom and just slide it or something, but you can do some kind of a, you can come up with some kind of a solution to actually show that to you, or you can, I don't know, squash it, everything into one and show the entire one.
Okay, thank you.
Mm-hmm.
Hi.
Hi.
Can you work also with, put this together with satellite imagery in the sense like counting things on satellite imagery and then working with them as features of your library?
Of rasters, basically.
For example, I don't know, counting swimming pools on an area or something like this.
From image.
Yes.
Yeah, so unfortunately not. We are more focused on right now we're more focused on the vector representations and getting the data from that. We have a loader for the tile loader. I'm not sure if I showed that actually, but you can get the tiles from OpenStreetMap or any other place that supplies you with the tiles and get the tiles. I'm not sure you have any methods to actually work on that, not yet. Yes.
Bitmaps of the tiles, but it's not.
Yeah.
It's vector rendered into that.
Yes. So OpenStreetMap doesn't have the satellite imagery. We don't support that actually at the moment. Yep. I saw one question over there.
Hi.
Hi. So,
is this a specific projection where areas are measured, or do you consider the spherical?
Yes. So this is what we've shown here is by default the WGS84 projection, which is a Mercator projection. No. Yes, some kind of a Mercator projector. You can try to project that to some other projection. Let me see if I can do that here. Yeah, so the area is skewed here, but you can transform it to another projection using GeoPandas. We don't like reinvent the wheel. The GeoPandas has the availability, the functionality in it already, and you can like do 2 CRS and put any other projection that you want. So, for example, some kind of a metric projection, or you have a projection only for certain regions or country. It's all available there. So you can do that. But that's WGS84 projection. Any other questions, maybe? Yeah, in the back.
Hi. You showed the embedding, and it's really nice human readable, but as it is meant for AI, do you plan on implementing some dimensionality reduction there?
Yeah, and these are other embedders that we have. So the count embedder is the simplest one. You can do some post-processing on your own on that. But we have Hextovac, Highway2Vac, or GTFS2Vac. These reduce the dimensionality, the dimensions a bit, and they are more like machine learning embeddings from machine learning world, let's say, not just counts of the particular features.
Okay, cool. Thanks a lot.
Thanks. Any question? Okay, yeah, thank you. That was very good questions. Thank you for that. Okay, and yeah, I talked about that. Any questions? Okay. I think that's all on my part. Thank you. Now we'll go to the machine learning example that will maybe facilitate or answer your question.
Okay, can you hear me? Yeah. Okay, so as Kacper gave you a brief introduction into our library, let's now use it in some real-world example and actually apply it in conjunction with some machine learning algorithms. So I have prepared for you a task. So let's design a bicycle sharing network system here in Basel, because there is no network, like you have multiple stations across the cities. You can rent a bicycle at any station, return it at any different city. So let's try to utilize the spatial data, use the SRAI to process them, train some model to design such network here in Basel. So apart from training the model, what we'll do here in the coming minutes, we will utilize a pre-trained Hextovac model. There was a question about more machine learning suited embeddings, so that's one of the models, which was actually designed by Szymon and published, I guess, 2 years ago at the SIG Spatial conference. Then we'll use these embeddings to train a classifier, which determines how well the region, the area is suited to host a bicycle sharing system station. And everything will be done with our library to gather all the data which is needed and process it to the form which is just ready to feed through the classifier. So what we'll be using here, everything from our library you have already seen described by Kacper. We have some loaders, regionalizers, embedders, and then just scikit-learn, simple scikit-learn classifier based on support vector machine. So here, let's start with the experiment description. So we'll say that our donor, our source city will be Wrocław. As a side note, the bicycle sharing system in Wrocław was actually designed partially by members of our team from Wrocław University of Science and Technology. They developed a model which proposed locations in the city, and then actually they were used to place the exact stations there. So we have like data-backed system in Wrocław. So let's try to train a model on the Wrocław system and apply it here in Basel. H3 resolution, usage of H3 cells is required by the embedder. Embedder works on H3 cells. So we use the resolution 10, which is roughly 300 meters in diameter, or even smaller, 60 meters. So we'll have quite accurate predictions of quite small areas and how well it's suited for a bicycle station.
H3 is not required, but nothing else was tested.
Okay, yeah, that's a disclaimer from the author. H3 is not required because it just utilizes features in the area, but it works on H3. It wasn't tested anywhere else. And we'll be downloading the locations of stations from the OSM. So first we start with getting the regions, the areas on which we'll be working. And we can start by downloading the locations of bicycle sharing system stations from Wrocław. Here they are, all plotted on the map. As you can see, there are more in the city center, some in the suburbs. They are aligned with some main roads, so it looks like a well-designed system. It actually works pretty well. In Wrocław, there's a lot of people using them. And then we use the Hextovac model. We have pre-trained some models. We'll be using the one trained on data from Polish cities. We selected about 70 cities, which are the major, biggest cities in Poland. You can download the model from our from this link that's in our library repository. So as I said, resolution 10, and here you can see that the model just works on those tags. So it utilizes this information from OpenStreetMap to generate this machine learning ready embedding. And we have over 700 different features. So let's just briefly translate, because we have just the list of features. We need to translate it into the query to the OpenStreetMap. So that's just some utility function, just split the name to create this dict that Kacper was showing earlier. And now it's time to load the data. I won't be doing it here now because it takes a little bit longer than I'd like to. But what we do here, first we load the data based on this, based on the query filter which we designed in the previous stage for the source area, which is Wrocław. So here we use the one of our loaders, and it gives us all of the features with these matching tags for the entire city. Then we split the city into the H3 cells using the Regionalizer. We join features with regions so that we can align them all together, and then feed it through the embedder. And it gives us for each of the regions the embedding, which is 64, has 64 values. And here, as you can see, they are more machine learning suited because we have no idea what they mean, which is quite a good indicator that they will work nicely for the model. So we have the embeddings for all of the regions, and now we go to, so we have the input data. Let's now have the output data. So let's find where in those regions we have bicycle stations. So again, we can use the same principle of joining some data, which is bicycle stations, with some regions, which we have already calculated, and we just merged it together to find where, in which regions there are bicycle stations. And now let's select the regions with stations in them. And as you can see, we have 223 regions which have bicycle stations in them throughout the entire city, and over 20,000 regions without, which is not a good case for any machine learning algorithm, because we will probably just say, don't put a station anywhere. So let's just do the undersamplings just to make it easier for us. Just a reminder, we want to design a bicycle sharing system in Basel in like 15 minutes. So let's make it easier for us. And here we can see that on the map how those regions are split. So we can see that in the orange ones are regions with bicycle stations in them, and some random regions without bicycle stations there. If we were to do this, like had more time, we should probably select these negative samples slightly better so that they don't land in the middle of a forest, in the middle of a river, so where no one would really put a station. But as I said, 15 minutes to design a network bicycle sharing network. Okay. And then, so we have the X's, which are the embeddings from Hextovac. We have Y's, which are just indicators whether there is a bicycle station in the area or not. So we have everything we need to train a classifier. So we just do the train test split so that we know how well our classifier works. And just train a classifier using one of the scikit-learn's ready-to-use classifiers. We have reasonable accuracy, I guess, for this amount of preparation done. So we have created successfully a classifier trained on Wrocław data, which predicts whether a region, a given area, is a good candidate to place a bicycle sharing station in them based on over 700 different features from OpenStreetMap. To do this kind of model by hand, it would be quite problematic, so this embedding part is really beneficial. And now let's transfer this model here to Basel to see how our network would look like. So we have to prepare some data for Basel. So here we repeat all of the steps which we done for Wrocław. So we split it into regions, we download features from the OpenStreetMap, join it all together, and feed it through the embedder. That's how you run it. And we can just run the classifier. And here we can see that the more red a region is, the better it's suited for hosting a bicycle sharing system station. And this actually is quite a valuable input for a company which wants to introduce such system in Basel, or for the government local which wants to design such system or order such system, because you don't have to go through the entire city. You just go to the regions with the highest probabilities and there select where exactly is the best location for a station. And you can always say that it's all done based on already existing, well-operating system in Wrocław. So there is quite a high chance that the regions with higher probability will be a good spot for to host a station, which will work nicely. And here we can see that we have some bias towards the center, which was also in Wrocław. There are more stations in the city center. We have some candidate locations on the outskirts, which is also something we want to do. And that's it. Congrats, we have created a draft for a bicycle sharing system here in Basel. Now we would just need to know the constraint, how many stations we actually can put. Just go to the city and put them there and make people enjoy bicycles and using them as a means of transport. And as I said, we have done it in like 15 minutes. So I would encourage you to see this link where you can see Camille's master thesis results, where he took this task more seriously. And he proposed a similar approach, but on a much larger scale and much better model. You can use the model trained on all European cities, most European cities, and design and see where it suggests locations, for example, in Africa, in Asia, any city in the world. I guess there are over 100 cities to select from. So I encourage you to check it out, and that's all from me. And if you have any questions, feel free to ask. Okay, I see the question back there. But please wait for the mic, because we're recording.
So by training the model, you assume that the location of the bike station is good. What if it is not?
Well, that's always, if you have garbage data, you have garbage model. That's like a basic principle. But as I said, what we do here is we transfer something which was already done in Wrocław to Basel. If it was done bad in Wrocław, we'll have probably equally bad system here. But that's a good idea because, for example, not every city, for example, smaller cities wouldn't have the resources to design the system from the ground up. And or if you look at over 700 different features from the area, which are buildings, benches, toilets, parks, schools, there are loads of different features used by Hextovac. So you just can spare all this time, resources, which you probably don't have in the smaller cities, and just try to adapt well, something which was designed and works. Because in Wrocław, it works, actually.
Okay, thank you.
Okay, I see also. Okay, yes, the question was about the difference between blue and orange spots. So this is just the visualization of our training data. So where we have the regions with stations, they are the orange ones, and the regions without, so the blue ones. So what we do is we take a single region, and we say, what is the probability of a station operating well in there? Is there a good chance that there should be a bicycle station? So then for this region, we download the data from the OpenStreetMap, all the 700 tags. We use the embedder to translate it into a vector embedding. And then our classifier predicts whether this region is a good candidate for a bicycle station. And what I'm showing here is just the visualization of which data was used to create this particular classifier which we're running in this tutorial.
Yeah, but the orange is where you already have a bike station, right? And the blue is what then?
Is a random region without a bike station. So that the model.
Okay, it could be anywhere on the whole map.
Yes, it could be anywhere. I just, as you can see here, if we were to put 20,000 samples which are of one class and 200 of other, I guarantee the model would just tell, don't put a bicycle station anywhere. That's why it's so scattered in the city. Yeah. Okay, I see another question there.
I have a question on the regionalizers. I don't know if this is a question for you or previous speaker, but can you choose the regions to have different size? So sort of weight them by population, for instance, so you would have inversely proportional size of your regions? Okay.
To select them, you would have to just do this manually, which parts divide with which size, but the embedder works for any data which you feed through it. So as long as you do this like consciously and you know what you're doing, that like from the perspective of the library, no problem.
Okay, very cool. Thanks.
Yeah, that's the, as Kacper is mentioning, it's the resolution parameter here. So you can just split your city like city center, suburbs, put different resolutions, and then everything works the same.
Okay, cool. Thanks.
So I don't see any more questions, and I know we have quite an interesting example from Kamil coming up, so thanks a lot. And if you have any more questions, feel free to ask them on Telegram.
Okay, so I should be heard now. Thanks, Piotr, for your nice presentation. Now I will go to here, the dot.
Emojis once again.
Let's go to the business use case. Stop and FNF. Yeah. Okay, so I will be showing you a market share analysis as a business use case with our library based on fast food restaurants in Prague, in Czechia. What we'll be doing is analyzing the local market share defined by the nearest restaurant to a particular Prague resident. And the analysis will use demographic data from the Czech Statistical Office with residential buildings and fast food restaurant positions downloaded from OpenStreetMap. So first, let us geocode the region of interest, which will be Prague in Czechia. So that's pretty straightforward. Now we will load the cadastral data, the demographic data from the Czech Statistical Office. This data has been already provided in our tutorial in form of GeoJSON file, but this has been derived from the source materials from the Czech Statistical Office. And here you can see the more yellow or green regions have more population than those regions with violet color. So we can just see the density of population basically in the regions. What we will do, we will download the residential buildings from OpenStreetMap and try to interpolate this population to assign an estimated population for each particular building, each point in the Prague where there's a building. So we'll download residential buildings from the OSM and use a number of flats defined by building flag tag in OSM as a way to interpolate the data more realistically. So let's do that. We'll use OSM online loader from our library, load for the Prague area residential buildings, and download also a number of flats as an additional tag. Then we'll filter out all the buildings that are residential and where number of flats is not null. And then we'll just parse it from string to number, because values in OSM are in strings only. And at the end, we want to parse each geometry to a centroid. So not every building, most of the buildings are defined by a polygon, but we just need a point in our example. So now we'll try to interpolate the population. There's a function written in helper module just for this tutorial, because the code isn't exactly a point of this presentation. We will take the regions, we will assign for each region what buildings are in there, and then we'll just using the number of flats, assign the population. Let me just maybe make command plus so to make it a little bit bigger. So in the end, we've got features with geometry. So each point in Prague, type of building, number of flats, and at the end, estimated population. We will leave it as floats, but maybe in your mileage may vary, and you might want to round it to an integer. But now we'll leave it as floats. So now to see where this population lives, we can see whole Prague in points. So where are the buildings basically, and here is the zoomed in version on the Prague center, and you can see singular dots which represent buildings. So there are over 90,000 buildings in Prague which are residential. Okay, and let's go to the next step. Now we will load data about fast food restaurants. Those are defined with tag amenity equal fast food. And in this example, we will just focus on KFC and McDonald's brands. So we'll just run those two cells. So we've got again, loader, the same principle as with the buildings. We just filter those that are in McDonald's or KFC brand. We got geometries as well. Let's go further. We will also map them to a centroid, because some of the restaurants are defined as a polygon. And using simple aggregation functions from pandas, we can see that we've got 37 McDonald's and 30 KFCs in Prague. So using those data as our seeds, we'll use the Voronoi regionalizer that has been shown in previous presentation. We will take those points. Voronoi regionalizer will generate a Voronoi diagram where we expect that each region just maps the closest area to a given seed point. That's a mathematical principle, but we have created an implementation that works on a sphere, on a globe, and not in 2D like currently existing implementations. So you can apply it to a whole globe without any limitations. And when we plot it, we can see that there's a more densely populated center. That's quite obvious. And then on the outskirts, the regions are bigger because there isn't so many restaurants available. So now we'll use spatial joins from GeoPandas. We'll just assign each building to a region that is created using restaurant data, and we can see that we've got for each region a geometry, a brand of a given fast food restaurant, and the total sum of population derived from the buildings we calculated earlier. And now we can again do some aggregation, and in the end we can sum all the population for each brand, and we can see that McDonald's covers 55.75% of the population in Prague, and 44.24% has closer to the KFC, which is maybe also quite logical because McDonald's has more locations, 7 more than KFC. And now we will plot this to analyze the area further. And we also have this utility function to just apply some colors, gradients, etc., and plot points. And you can see in red regions where the KFC has closer population, and in yellow the regions where the McDonald's wins, so to speak. And you can see the darker the color, the more population there is in each region, which is also logical because those regions are bigger, so maybe more buildings are within those regions. And using this map, you can, in business use case, see where are the so-called white spots, where there's no restaurant, so maybe on the outskirts down here, or maybe McDonald's might take some of the KFC population, putting a restaurant over here. And calculating the percentage is a common way to see a key performance index indices in businesses. Let me see what the time is. We got 15 minutes. So maybe to show you that it's quite easy to use it in other examples. Let me just this, not that. Here. We will just swap the fast food example to the cafes example using Starbucks and Costa brands. Not this one. Here, we will just run it, run all those cells again. So we've downloaded 24 Starbucks, maybe just plus to make it a little bit bigger. We've got 24 Starbucks and 24 Costa Coffee points downloaded. We've generated new regions, and the split between those is a little bit closer than with fast foods. We've gone to 51 versus 38%, so almost 50-50. And here is the map for the final market share. And yeah, this business use case is quite easy, so that's all from my side. And if you have any questions, I can answer them here. Oh, I can see. hand.
Thanks. So here you just assign based on direct distance as the bird flies, but it's not how humans travel. Can you do this also based on like actual distance on the road or time?
There are available algorithms to use road network. Those basically work on a smaller scale because you have to download all the roads for a given region, and it's quite computationally intensive. So on a bigger scale, this option just works. And we have a plan to incorporate the use case you're talking about with street networks. But yeah, that's in the working right now.
Thanks.
Okay, so if there aren't any more questions, do you want to? Oh, the third one? Okay, so Kasper tells me that there's enough time to show you the third example with supermarkets. So let's do that. Just uncomment this one with 6 top supermarkets in Prague. And let's just run all of those cells. No. So we've got a lot of points, 78 supermarkets from Albert and 10 from Tesco and the rest in between. Just running this Voronoi regionalizer gives us 226 regions. So that's a lot of densely populated regions visible here. And by plotting it, just click here and maybe minimize it. We've got a little bit more cluttered map visible with 6 different brands. And yeah, that's quite easy to scale up with thousands of points basically, because we are using multiprocessing under the hood to speed up the process. Zoom in to the center. Okay, so yeah, those regions can be analyzed, and you can send someone if you need to check the region, if there's a place to create a new shop, and yeah. Okay, so thank you. And now, Simon, you want to finish the tutorial?
Okay, can you hear me? Does it work? Yeah, I think it does. So, yeah, we've seen some interesting presentations. I hope they were interesting about different things, covering our library, some of the machine learning examples, and also some more of a geo-data analysis, I would say, from Kamil. And the thing is, we started this project as from the ground up from our master thesis, and just because we found that the domain isn't really well saturated, isn't easy enough to work with. I guess that there aren't many people. Well, it's hard to get into it. It's much easier, for example, to start working with NLP nowadays. And so, we started this project to try to make it easier for people to join the community, to contribute, and to maybe also to push the scientific community towards a more open science, because we see a lot of public publications, I think specifically from Asian countries, where there are, I would say, very, very brilliant methods being published, but they are, I don't know, for example, being evaluated on closed data sets, or the benchmarks aren't there. And the problem is that it's hard to join, and it's hard to start working on something else, to compare your method to other methods and so on. There aren't enough benchmarks data sets, and there isn't enough tooling for GeoAI. That's our belief, I would say. So we started the project. We'd like to encourage you, if you work in geospatial data, we'd like to encourage you to maybe contribute. We've already got a contribution from Max here that's in the workings. He wanted to implement a method called Geovac, an embedding method, and we are reviewing that right now. So if you've got some code lying around, no idea for what we could do better, what's your pain point in working with geospatial AI, if you do, you can let us know. You can also reach us. I think, yeah, we opened a discussion for it. So we encourage you to check the library out, check the discussion, maybe contribute if you can. We would be we would be grateful. And yeah, now for the cheesy quote. We think that geospatial data needs its Hugging Face moment, just to make it easier for everyone to contribute and follow along. So it's very easy to publish a data set on Hugging Face. Yeah. So we'd like to do the same in geospatial data, but it really isn't that easy to do that on Hugging Face, for example. Maybe there should be an extension of Hugging Face for, well, we don't say that our approach is the best. We'd like to know what you think, and we'd love to push the research further. Yeah. So if you've got any more, well, no, I don't think, I think it was already shown, and this is actually too big. There is a Telegram channel if you want to ask some questions or join the discussion. You can reach us in different places. We'll be here till Sunday, I think. So you can find us and talk about anything from geospatial to NLP to road cycling, I think. Yeah, and that's it. Thank you.
I have a question, actually. How does your work... So GeoPandas is yours as well?
No.
OK. How does it correlate with CartoPy, which does something that looks kind of similar in some ways?
Can you help me out here?
Yeah. Just quickly.
OK, so let me just turn this off.
OK. So CartoPy is a Python library to interact with Carto location intelligence toolbox that is paid for first of all, and the library itself is free. Well, with CartoPy, yeah, with the Carto library works with the Carto.com location intelligence toolbox, and yeah, that's what I remembered. You didn't mean CartoPy like plotting stuff, or exactly that, the CartoPy for plotting, or the Carto frames for the Carto page?
So we have people at my institute that use CartoPy,
and
they do something that supersedes this, but I fail to see the distinction here, because they do similar things, but with CartoPy.
So the library itself is open source, but you have to have an API key to access the Carto toolbox in the cloud, working on BigQuery, AWS, and Snowflake, from what I know. The Carto.com toolbox. As a data source and functions that are in there. Some of them are open source, but most of the more complicated use cases are behind the paywall. Okay.
Okay, there's one more question there, I think.
Thank you very much for the presentation. I have a question about the embedders, the embedding methods that are pre-trained. Can you give us a bit more details on how you pre-train them, what kind of objective function they minimize?
Sure. This is a bit more technical on the research side, I would say, but sure, we can go and see. So maybe go through here and showcase the site as well. So we've got the site for the research lab, and we've got all our publications here. And so I think we've shown the most about Hextovac, right? So let's try this. Oh, there are a lot of images there. So yeah, but to start, Hextovac works by taking the idea from Word2Vec and FastText, I would say, and the assumption that things that are close are more closely related to one another than to other things that are more distant. So we assume that representations of things that are close should be close together and should be farther away from the representations of distant objects. And so we regionalized the areas into H3. We took the features from OpenStreetMap. We counted the features, and the dimensionality reduction, or the objective function there, was to try to minimize the binary classification target of trying to predict whether two regions are neighbors, so whether they are or not, 1 or 0, using the same embedding feed-forward network. So this is it, and you can check that out in the paper.
And so this representation is only for a specific resolution of the H3 thing?
Yes. Yes.
I plan to have some kind of hierarchical representation natively in the pre-trained model?
No, unfortunately not. Because I think, well, you can train separate models for different resolutions, but I would assume they wouldn't work as well for different resolutions, just because the number of objects that are in smaller cells are smaller than in larger cells. So the representations could just easily follow the distribution there. Well, yeah, I would say that you could aggregate up. So use the H3 hierarchical representations and maybe do something like mean representation of the bigger cell. So utilize that. Yeah, so that was Hextovac, and then there are two more, which I wouldn't go into details there, but you can check them out here on the page. It's all there, and I think nothing is behind the paywall. At least there is a preprint. Yeah, so that's cool. So you can check it out here, and I think we have no more time, or I don't know how it works right now. And also because I'm not really sure. I'm not the author of the other two methods. Yeah, sure. Okay, so thank you once again, and have a nice stay in Basel.